Hello again. In this video, we're going to get started on the new unit packet. So I will post the unit packet on the Google Classroom, and hopefully you can download it and make a copy and then take notes as we go through the unit packet. Now, you are going to download it and you're going to think, oh my God, this is such a large unit packet. Well, it's not that large in the sense that primarily the unit packet has practice problems. And some of these practice problems are large in size, and so you might have maybe 5 or 6 problems in one single page, because part of what we're going to be doing is drawing figures, drawing molecules. And some of you have an artistic sensibility, and maybe you will enjoy when we get to that point. So I think it's a lot of fun, is how do molecules, how do they optimally shape themselves in three-dimensional space. So here we have 2 moles, and they're fighting over this molecule in the center, and that's the idea, is there's a competition in covalent bonding, and particularly between the electrons that they're sharing. So as we talked about before, we have 3 types of bonding: metallic. Let me change this so that you can see it. I'm not sure how to change it so that you can see it. Sorry about this, guys. I'm not used to doing what we're doing. Maybe up here. Oh, there it is, right here. So I'm going to make that black. There we go. Okay. Metallic is a metal bonded to a metal. Ionic bonding is a non-metal I'm sorry, it's a metal, right? Metal bonded with a non-metal. And then finally, what we're talking about now is covalent bonding is a non-metal bonded with a non-metal. And you can't see it. Sorry about that. Put it right there, non-metal. Okay, so let's get started. And I'm going to make that a little bit bigger if I can. Okay, we already looked at this curve if you watched my previous video. So as 2 atoms are moved from far apart to close together through section C of the curve, we can see we have separate atoms, non-metal atoms. They're coming together. As they travel through this upper part of the curve up here, does the potential energy of the 2 atoms increase or decrease? Well, you can see that it's decreasing because it's getting lower on the scale over here. It's decreasing, and as it decreases, it's giving off energy. It's providing energy to the outside because it prefers to be closer together. So put decrease in the first blank. Does the stability of the arrangement increase or decrease? As it falls down the hill, it increases. Stability increases. Which electrostatic force? Proton-electron attraction or proton-proton repulsion? Well, it's an attractive force, so proton-electron attraction increases. Proton-electron attraction is what causes this change in stability. So down here, I'm going to write down the negatively charged electron is a electron from one non-metallic atom is attracted to the, ran out of room, I think, positively charged nucleus of the other atom and vice versa. Did I spell vice right? Versa. Okay. As the two atoms are moved, let me bring it down a little bit. As the two atoms are moved closer together, too far apart through section A, and that's this side of the curve, as we try to force them even closer together, does the potential energy of the two atoms increase or decrease? It increases. Increase, right? You have to push it together because they're repelling each other. The nucleus of the two atoms are so close together that they're repelling each other. Does the stability increase or decrease? It decreases. Decrease because they're just too close together. Which electrostatic force? Well, in this case, it would be proton, proton. Proton, proton repulsion. So I'll put the positive charges of the nucleuses of each atom is too close together and they repel. Okay. The next set of questions concerns the graph on page 193 of Holt Chemistry, and this concerns bond energy. Actually, it was a table. The bond energy for two bonded atoms is inversely proportional to the length. Inverse. What that means is as the bond length decreases, the bond length increases, the bond energy increases. As the bond length gets smaller between the two atoms, the bond energy increases. And as the bond length increases, the bond energy decreases. Okay. I don't know what happened to the font there, but anyway, the size of an atom measured as the atomic radius is a periodic property. That means it changes either bigger or smaller depending on where you are in the periodic table. There's a distinct pattern of change in the atomic radius moving across a period of the periodic table or down a group. Describe the trend in the atomic radius for moving from top to bottom through a group on the periodic table. So from top to bottom, if you can imagine the periodic table as a series of columns up and down and rows left and right. The columns are also called groups. So as you go from top to bottom, what happens? Well, as you go from top to bottom, the atoms get larger. Get larger because you add an entire energy level or period of electrons each time you, I'll get this right, hold on. Each time you go down a period or energy level. And what does this do? Well, it this puts on an entirely new layer of electrons, making the atom I'm trying to type too fast. Larger. Okay. Explain why this trend exists in terms of atomic structure, shell size, and or number of protons. I think I answered that in part A. Okay. What next? Okay, I'm going to stop here for this video. So that's a good introduction to what's going on in the size of atoms as they get larger and smaller based on where they are located in the periodic table. It also talks about covalent bonding and the energy changes that are going on as nonmetals come together and share electrons. When they share electrons, there's an optimal distance that balances the repulsive forces between the two nucleuses, positively charged nucleuses of the two atoms, and the attractive forces between the electron of one atom and the proton and the nucleus of the other atom. And they achieve a stable arrangement where they're just the perfect distance apart that optimizes those forces, that cancels out those forces just right. Okay, so I'll talk to you on the next video.